Identifying dark matter is one of the greatest challenges in cosmology. 90% of the matter in the universe is dark, but we can only speculate about its nature. The leading candidate for dark matter is some variety of very weakly interacting elementary particle. This candidate must interact with the material in the universe in a way that is much weaker than the proton, a basic constituent of all matter. This weak interaction of dark matter explains its apparent behavior in the universe. When a cloud of dark matter and ordinary matter contracts to form a galaxy, for example, the ordinary matter eventually fragments into stars, but the dark matter is left behind. Its weak interaction also means that dark matter particles do not lose energy by radiation, and hence their darkness. During cosmic evolution, dark particles condense into dark clouds, but not into stars. Dark matter is pulled by gravity alone. In our observations today, we find dark matter both in the inner regions and outer regions of galaxies. In our own Milky Way galaxy, for instance, there is an increasing concentration of dark matter in the inner galaxy, in contrast to the way ordinary matter dominates in regions that include our solar system, which is ordinary matter orbiting our sun. Dark matter also populates the outer regions of galaxies where there are fewer stars. Dark matter dominates the mean density of these outer regions. Nevertheless, these stars, far from the galaxy center, continue to maintain their orbital velocity. If the distribution of the dark matter were traced by the stars, the circular velocities would decrease as the gravity field gets weaker. The dark matter is much less concentrated than the starlight. Dark matter consists of weakly interacting elementary particles. We know that any particle that can exist, according to the laws of physics, once did exist in the fiery furnace of the Big Bang. All particles have antiparticles of the opposite charge. Today, antiparticles are exceedingly rare, but in the first instance of the Big Bang, every particle coexisted with its antiparticle. There was complete symmetry. This changed, however, as the universe cooled down. The primordial furnace left behind very little antimatter, which is fortunate for us because an encounter between a particle and an antiparticle results in total annihilation. No matter survives. The amount of surviving antimatter depends only on the strength of the interactions of the particle in question. An antiproton is strongly interacting. Many were once present. Pairs of protons and antiprotons were created spontaneously from radiation at the extreme temperatures encountered in the first nanoseconds of the universe. In fact, the universe was once dominated by proton-antiproton pairs. As the universe expanded and cooled, spontaneous creation stopped. Almost all of the antiprotons annihilated with protons. But fortunately for us, some protons are left behind to form the material universe. This great annihilation produced the cosmic microwave background we measure today, the heat left over from the fireball at the beginning of the universe. The same logic applies to the dark matter particles. Most had annihilated, but in this case far more were left behind because these particles interact so weakly. At this point in our exploration of the dark side of the universe, we discovered a remarkable coincidence in how the forces of nature seem to work. This kind of discovery always makes cosmologists feel good inside. Americans Ben Lee and physics Nobel laureate Steven Weinberg discovered that the leftover abundance of weakly interacting particles was just what is needed to account for the dark matter. There was no reason whatsoever for this coincidence. Nature just prescribes it. Weakly interacting particles can actually account for all of the observed dark matter if their interaction strength is typical of the weak nuclear force. They must, of course, be long-lived and interact with a strength similar to that of the neutrino. This seems a natural interaction strength to be expected for such particles. The explanation of the origin of the weakly interacting dark matter soon became even more compelling. A new theory, called supersymmetry, was developed that postulated the existence of hundreds of possible dark matter candidates. Recall from an earlier chapter that symmetry was the point at which the universe was so hot that nothing was separated, as when we melded a Rolls-Royce and Volkswagen together so that their basic chemicals were the same. In the new supersymmetry theory, any candidate for dark matter must be a weakly interacting particle. Only one of the candidates can be the real thing, however, and in fact it must be the lightest of the supersymmetric particles so that it is sufficiently stable. The rest of the candidates live for only nanoseconds. We are now hot on the trail of these particles. One of the primary goals of the Large Hadron Collider, operated by CERN on the Franco-Swiss frontier, is to search for evidence of supersymmetry. The circular accelerator, which runs for 17 miles, will seek one-sided jets in high-energy proton-antiproton collisions. The collision releases energy that in turn creates cascades of quarks and other short-lived particles. Momentum must be conserved in the collision. Seeing a jet of particles emerge in one direction with no corresponding jet spraying out in the opposite direction would provide evidence for supersymmetry. As noted earlier, there are many candidates for the dark matter. Fortunately, the most popular class of candidate particles hails from the theory of supersymmetry and is likely to be observable, provided that supersymmetry is correct. The lightest supersymmetric particle is expected to be stable and can account for the dark matter density. Supersymmetry is motivated by theory, but also by empirical arguments. One of these is the running of the coupling constants of the fundamental forces. The constants are very different from each other today, but this was not always the case. Today we live in a low-energy universe, but at very high energies, the weak nuclear force becomes much stronger. When we extrapolate the strengths of the different forces measured at low 100 giga-electron volts energies, they seem to converge near 1,000 trillion giga-electron volts. Supersymmetry requires convergence at a precise energy, which is called the scale of grand unification of the fundamental forces. As we saw earlier, this scale provided the stimulus and natural setting for inflation. Again, the candidate particle must be neutral and weakly interacting. It is referred to as the neutralino and is the heavy counterpart of a known particle such as the photon. Neutralinos are in thermal equilibrium at the high temperatures of the very early universe. As the temperature dropped at the beginning of the universe, a relic density of all the stable particles survived. The weak nature of neutralino self-interactions resulted in a large relic density, in contrast to that resulting from strongly interacting particles. Remarkably, the relic density generically gives an approximately critical density of dark matter for a weak-like cross-section. The universe was once at energies where supersymmetry prevailed, and hence a breeding ground for supersymmetric dark matter. This means matter and antimatter. The primordial furnace must have created pairs of weakly interacting particles and their antiparticle partners. Particle theory gives us candidates for these particles. None have actually yet been observed, which is a minor obstacle. If one of these new particles is stable, then its weak interactions guarantee a large survival fraction today. These could be the elusive dark matter. Now we can understand why there were so many dark matter particles left over from the Big Bang. We are trying to find this dark particle by the use of massive machines using state-of-the-art technologies like the Large Hadron Collider, but this project alone cost some 5 billion euros. The collider has put together thousands of superconducting magnets in order to produce a particle accelerator that, in its circular ground plan, is 5 miles in diameter. Obviously, a machine like this can become so expensive that we reach the earthly limit for such research. Fortunately, therefore, we can still use the universe itself as a particle accelerator. In the reaches of the universe, particles are annihilating and stream across space. We are bombarded with dark matter. About 10 million particles per square meter per second pass through us. As we will soon see, we don't always have to build a super collider. The universe itself provides a poor man's way of searching for dark matter. The dark matter that bombards us is produced by the annihilation of particles, as if crashing in a super collider, in the distant universe. How is this taking place? Once, in the very early universe, the dark matter particles were far more numerous and annihilations were frequent. Today, the density is low, and annihilations of the dark matter particles are very rare. But although rare, because the volume of each galaxy halo is so large, annihilations may still lead to a detectable signal. Hence, our best target is the debris from particle annihilations. Typical particle masses are expected to be on the order of the energy scale characterized by our current theory of supersymmetry. This scale is between 100 and 1,000 proton masses. The acronym for these weakly interacting massive particles is WIMPs. When annihilations take place, they produce a shower of energetic elementary particles, most of which decay immediately. The stable products are high-energy gamma rays, proton-antiproton pairs, neutrinos, and electron-positron pairs. All of these are potentially observable with future experiments. The predicted flux depends on the density of dark matter. We infer the local density in the solar neighborhood from the rotation of our galaxy. It amounts to 1/3 of a giga-electron-volt per cubic centimeter. Some 10 million per square meter per second pass through the Earth. Nothing beats direct detection. This enormous flux of weakly interacting particles illustrates the nature of the research challenge for the future. With such a great influx, we can try to achieve a direct detection of the particles. In direct detection techniques, the dark matter particles, although very weakly interacting, do occasionally collide with atoms in a device, the detector, that has a special highly sensitive material to pick up a slight trace from particle collisions. But this direct detection does not work with other kinds of dark matter annihilation, so we use indirect detection as well. This technique picks up the occasional dark matter annihilations in a galaxy halo. When these annihilations occur, they produce an energy loss in the form of both gamma rays and energetic particles. Our detection of these is indirect confirmation of dark matter. Both kinds of detection are giving us hope to solve the dark matter puzzle. It's also a fascinating story of technique and technology. So let's look more closely at both of these approaches, beginning with direct detection. Clearly, there is no substitute for direct detection of the dark matter particles. The flux of such particles at the Earth is relatively large. Of course, the interactions are weak, but elastic recoils leave potentially detectable signals in sufficiently large masses of target material. The nuclear recoils heat and occasionally ionize detector nuclei. Detectable signals include seeing traces of electrons and ions as well as pulses of vibrational energy that occur in the atomic lattice structures of all solid materials called phonons. However, there are important backgrounds, especially resulting from cosmic rays hitting the detector and producing neutrons. To see the WIMP signal, one has to suppress these backgrounds. The only way is to go deep underground. Disused areas in mines have been used. One of the most effective is in Sudbury, Canada, at a depth of 3 kilometers. Until recently, detectors in underground laboratories have been kilogram scale, with sensitivities to elastic scattering cross-sections down to a 10/1000th of a barn, or 10 to the power of -24 centimeters squared. 1 barn is the typical interaction cross-section for ordinary atomic nuclei such as protons. It corresponds to an effective area for scattering amounting to the square of the classical radius of a proton. These are the strong nuclear interactions. For there to be a significant density of WIMPs surviving from the very early universe, the typical interaction strength must be less than a billionth of a barn. This is the domain of the weak nuclear interactions. These are the reactions that involve neutrinos. The experiments have ruled out WIMPs in this regime. However, the supersymmetric model parameters allow a significant density of dark matter over a wide range of interaction strengths, below those of normal weak interactions. One can still have WIMP dark matter for cross-sections up to 3 orders of magnitude lower than current experimental limits from WIMP searches. Theory has shifted the goalposts, and more sensitive experiments are required. The only way forward is to have larger mass detectors. Ton or even kiloton detector masses are required to probe the full range. This is the goal of the new generation of experiments that use detector materials as varied as liquid argon and xenon or crystalline germanium. One intriguing development has come from the realization that the dark matter may possess fine-scale structure on the scale of the solar system. The dark matter is cold, in the sense that individual particles have essentially no random motions. If fluctuations are present initially, the dark matter responds to gravity on scales much smaller than those of galaxies. Indeed, the smallest clumps expected to have Earth masses, but are much more diffuse than a planet. Consequently, the Earth, as it orbits the Sun, occasionally runs into dark matter clumps. The dark matter is so diffuse that it has no direct influence via impact on the Earth. However, experiments searching for the weak signal from direct detection would find an annual modulation of the elusive signal. Streams of dark matter in the solar neighborhood result from the incomplete tidal disruption of dark matter clumps in galactic orbits. One direct detection experiment at Gran Sasso, a deep underground laboratory in Italy, makes use of this signature and is the only experiment to report a claimed detection. This experiment, called Libra, utilizes a vast vat of sodium iodide and searches for light scintillations. Other groups dispute their results, however, using different techniques and more sensitive experiments. A window remains, however, if the neutralinos interact coherently. In this case, the interactions depend on the direction of spin of the target atomic nucleus, which can be important for nuclei with odd numbers of particles. Very few experiments are sensitive to this interaction. The most important case is hydrogen. The Sun can trap such WIMPs, and its structure is very slightly affected. If the mass is around 5 proton masses, the WIMPs take a long time to settle into the core and annihilate. They basically fill the Sun. The usual lower bound on WIMP mass is about 50 proton masses from accelerator limits. But some models permit these lower masses. Low-mass WIMPs turn out to be a possible means of reconciling Libra with most of the other experiments. These WIMPs scatter with solar particles and slightly modify the temperature profile by redistributing the thermal energy. There are 2 techniques for measuring the internal temperature in the Sun. One involves detecting the neutrinos emitted in the thermonuclear reactions that occur in the solar core. The successful detection of solar neutrinos has confirmed that thermonuclear burning of hydrogen powers the Sun. It also fixes the central temperature to high precision. Another experiment involves detecting seismic quakes in the Sun. Helioseismology measures very slight vibrations of the Sun. The frequencies of the measured modes depend on the sound crossing time in the Sun, and therefore on the temperature profile. At present, our best model of the Sun cannot account for the helioseismology results. The discrepancy is only about 10%. However, the conclusion is that despite the Sun being the closest star and exquisitely well studied, we still lack a complete understanding of its structure. Dark matter may conceivably have a role to play, although it is far more likely that the discrepancy lies in something as mundane as our modeling of turbulence inside the Sun. As we described earlier, our indirect detection of dark matter is achieved by tracing the pieces that spray off other particles when they collide with dark matter. When dark matter particles of 100 to 1,000 proton masses collide with other particles, the annihilation produces energetic gamma rays, neutrinos, positrons, and antiprotons. All of these are distinct signatures that can be observed against a known background. High-energy positrons that emerge from collisions, for example, are especially useful since they are a rare component of the galactic cosmic rays. Moreover, all of these byproducts of the collision look different from relics of the dark matter since those relics cannot exceed the WIMP mass. This contrast leads to a feature in the energy distribution of the high-energy photons or particles. Other particle backgrounds are blind to WIMPs, and so the backgrounds do not show any features that might indicate the presence of WIMPs. Despite the many candidates for the lightest supersymmetric particle, we know its annihilation cross-section to great accuracy. This stems from the requirement that the WIMPs account for the density of dark matter. If the cross-section is too low, there are too many WIMPs. If it is too high, there are too few WIMPs. This constraint arises because annihilations in the early universe fixed the surviving density of WIMPs. The WIMP particle so far is undetected, which of course means that its mass is unknown. However, the supersymmetry theory specifies a range of cross-sections at any given mass. This range spans some 3 factors of 10, while the allowable mass range extends from only 50 gigaelectronvolts to 1 teraelectronvolt. The inference is that experiments must cover a wide range of sensitivities to have any chance of detection. However, detection at some level is guaranteed if the lightest supersymmetric particle is the partner of one of the known particles, which themselves are classified according to their spin and mass into particles such as bosons, for example protons, or fermions, which include electrons and quarks. The positrons provide a promising signal because cosmic ray positrons are quite rare. The positron flux is controlled by the local dark matter density. The gamma ray flux is also an interesting signal. The halo is transparent to gamma rays. Because the density of dark matter is higher toward the center of the galaxy, the gamma ray flux is boosted. There are gamma rays produced by the interaction between cosmic rays and interstellar gas. There are also positrons in the galactic cosmic rays. But the dark matter signal should stand out. Its positrons and gamma rays have a unique distribution of energy determined by the mass of the annihilating particle. Detection of excesses in both the positrons and gamma rays relative to the known backgrounds would be smoking gun evidence of dark matter particles. Experiments carried out far above the surface of the Earth have been performed to look for positron and gamma ray evidence. It is necessary to go into space because there is too much contamination by cosmic rays interacting with the Earth's atmosphere. So far, there is no definitive indication of a signal in either gamma rays or positrons that could be from dark matter. There are, however, hints of possible detections in both cosmic ray positrons and diffuse gamma rays. For example, high-flying balloon experiments reported an anomalous spectral bump feature in the positron flux that is not explained by the featureless secondary spectrum of positrons generated by cosmic ray interactions with interstellar matter. The dark matter particles annihilate into a shower of debris. Consequently, the annihilations yield a positron feature centered around 10% of the particle mass. However, the data was not very convincing. The uncertainties are large. It is too premature to make much of any possible annihilation signal. New experiments are underway. A new experiment on an Italo-Russian space satellite launched in 2006 called Pamela is taking data that after several years in orbit is providing a much improved measurement of the positron flux. Early results support the anomalous spectral bump, but the interpretation of this feature cannot necessarily be interpreted as a dark matter signal. The strength is much larger than expected from the simplest theories. The alternative explanation appeals to a nearby pulsar in the constellation of Gemini called Geminga, an abbreviation for Gemini Gamma Ray Source, that is known to be a source of very high-energy gamma rays. More data will be needed to better understand the experimental results, and it will be necessary to find complementary signals. The most promising of these comes from diffuse cosmic gamma rays. Gamma rays from space have also been detected. Indeed, the Milky Way glows in gamma rays that are produced as cosmic rays pass through interstellar gas clouds. High-energy collisions between protons generate gamma rays. The Compton Gamma Ray Observatory detected an excess diffuse flux of gamma rays from the innermost galaxy. The energies of these gamma rays seem to be higher than expected from the flux predicted by cosmic ray interactions with interstellar gas. More exotic decay channels may be indicated than would be achievable with cosmic ray protons. This is just what is predicted for the WIMPs. The available decay channels for WIMP neutralino annihilation involve massive quarks, which weigh up to 5 proton masses. The resulting gamma rays from decays of these quarks are more energetic than those produced when protons collide with other protons. However, the data needed to be confirmed. The Gamma Ray Large Area Space Telescope, named Fermi after Italian-American physicist Enrico Fermi, was launched in May 2008 and should provide the necessary confirmation if WIMPs are indeed the elusive dark matter. The Fermi telescope provides an improvement in sensitivity by a factor of 100 over the previous gamma-ray satellite experiment flown on the Compton Gamma Ray Observatory. This experiment will greatly improve on the existing data. It should be possible to confirm or reject the reality of the possible signal from annihilating WIMPs. If the preliminary early results were to be interpreted as due to WIMP annihilations, a serious issue arises concerning the strength of the predicted gamma-ray and positron signals. What has been, possibly, observed is far larger than expected. A uniform dark halo falls short by nearly a factor of 100 in accounting for the observed fluxes in terms of plausible annihilation rates from the known dark matter density. There is a resolution of this dilemma, at least for the gamma rays. Clumpiness and spikes. In our search for dark matter, cosmologists must also contend with two other kinds of phenomenon, which can be helpful in our detection of the mysterious particle. One of these is the clumpiness of the dark matter, and a second is the way that dark matter spikes when it is in the vicinity of a black hole. The clumpiness of dark matter is related to its ability to provide the earliest pattern for the observed large-scale structure of the universe, which develops later. In the very early history of the universe, the WIMP particles decoupled from the radiation, which means that in the recent past, the WIMP particles were completely cold. That is, they had negligible random velocities remaining from their thermal origin. As the universe expanded, random motions of particles would decrease, and the WIMPs would become cold. This is the connection between cold dark matter and large-scale structure. The detailed clustering properties can be reproduced in computer simulations if simple models for galaxy formation are used. However, the cold dark matter candidate has not yet been detected. It remains a hypothesis. One uncertainty in computing the flux is the degree of clumpiness of the dark matter. For now, we work on the assumption that the annihilation rate is proportional to the square of the density. Numerical simulations of galaxy formation show that halos are clumpy, with up to 10% of the dark matter being in clumps, which can result in a large boost factor for the annihilation flux. The theoretical modeling of the halo tells us that it is highly clumpy. In a clumpy halo, there are far more particle collisions and annihilations than in a smooth halo. It is quite easy to account for the observed gamma-ray flux in this way. The positrons cannot be so easily explained because positrons scatter frequently as they propagate in the interstellar medium. The observed positrons cannot come from very far away, and certainly not from the inner galaxy, where the enhanced density and clumpiness of the dark matter boost the observed flux. The positron story must be more complicated, depending on how the positrons propagate and accumulate. The flux of the annihilation signal is sensitive to the minimum clump size, about the size of an Earth mass for typical WIMPs. However, interactions with stars will tidally disrupt many of the clumps, effectively depending on their orbits. Clumps with orbits highly inclined to the disk should survive. Low-mass clumps are only visible via their annihilation signal, which is obtainable by the indirect detection method. We have only mentioned black holes briefly so far, but now they become an important factor in detecting dark matter as well. Dark matter is concentrated in the vicinity of a black hole. Furthermore, relic spikes of dark matter develop around forming black holes. Dark matter particles are enhanced in number in the locally increasing gravity field. The dark matter density is increased near the black hole. So is the annihilation signal. We first need an overview of black hole formation. Their formation requires matter that can lose energy as it collapses. Baryons can do this by radiative cooling, but dark matter cannot, so it does not become material for the black hole. But, as the baryons aggregate to form the black hole, some dark matter particles invariably are trapped by the increasing strength of the local gravity field. The annihilation flux may be greatly boosted near a massive black hole that forms in the nucleus of a forming galaxy. These black holes are expected to form by way of accretion of baryons onto a seed black hole, one that is just sprouting, so to speak. The seed is formed from the debris of massive stars. This is not the only formation possibility, and another route to massive black hole formation is via runaway mergers of stars. We observe indirectly the phase of black hole growth as the consequences of gas accretion. The luminosity of the black hole increases as it is refueled by infalling debris. We infer the amount of fueling, since this is the phenomenon that powers quasars and active galactic nuclei. We have other clues about how black holes form and their relationship to dark matter. One is the fact that supermassive black holes usually show up in the spheroid or large bulge at the centers of galaxies. This seems to be a universal phenomenon. A substantial fraction of the mass of a spheroid is dark matter. When the central black hole of a spheroid formed, it must have concentrated the local dark matter in its vicinity. The weakly interacting dark matter responded to the deepening gravitational potential well around the black hole. A density spike of dark matter developed within the gravitational sphere of influence of the black hole. In looking for dark matter spikes, we naturally recognize that black holes form with a wide range of masses. The smallest dark matter clouds in which baryons can cool amount to about 1 million solar masses in weight. The most massive correspond to the largest galaxies. The corresponding black hole masses range from 1,000 solar masses to a few billion solar masses. All of these black holes develop dark matter spikes, or cusps. Black hole mergers destroy these nearby cusps of dark matter. Hence, it is unclear, for instance, whether the 3 million solar mass black hole at the center of the Milky Way possesses such a cusp. If this were the case, the annihilation rate would be greatly enhanced in the vicinity of the central black hole, and this annihilation rate would be detectable via gamma-ray emission. But not all black holes move to the center of galaxies. For instance, during the hierarchical buildup of the Milky Way, which involved merging together clouds of dark matter and baryons, the smaller black holes did not merge into the central black hole. These intermediate mass black holes remain in orbit in the inner galaxy. They are ubiquitous, and they are potential targets to detect dark matter spikes. Black holes are frequently ejected from the centers of galaxies, perhaps into intergalactic space. A merger of two black holes often ends with a one-sided burst of gravitational radiation. The net result is that the merged black hole receives the equivalent of a kick in the opposite direction, since momentum is conserved. The acquired velocity is often large enough to eject the black hole from its host galaxy. These intergalactic black holes should still retain some dark matter in their vicinity, although merging tends to weaken any initial spike of dark matter. The spikes should survive around intermediate mass black holes that have not undergone merging. These 1,000 solar mass black holes are relics of the initial clouds within the first stars that formed. The most massive of these clouds would have cooled as the emitted radiation from hydrogen atoms that are excited by collisions with other atoms. This so-called Lyman alpha emission and the efficient cooling associated with this type of cooling, which requires only atomic hydrogen, would have facilitated gas accretion rates onto forming protostars. The enhanced accretion implies that the first stars were necessarily massive. Massive star collapse facilitates the likely formation of 1,000 solar mass black holes. The most massive black holes in the universe power up ultraluminous quasars. These are the biggest black holes, and their masses exceed a few billion solar masses. They are found in the early universe at a redshift of 6 or beyond. These black holes are so massive and in place so early that intermediate mass precursor black holes must have existed in order to explain their formation. These intermediate mass black holes could be the missing link between primordial clouds, primitive early states, and quasars, which formed later around the largest black holes. As noted, most of these smaller black holes failed to merge into the larger ones and so are leftovers. In general, the merging process is notoriously inefficient anyway. Many smaller black holes would be ejected by recoil in the form of binaries, which are black holes in orbit about each other, and then simply be dissolved as the larger systems grow. But as many leftover black holes survive as are dissolved, and these are the relic black holes that we believe populate our halo. Added up, these intermediate mass black holes are expected to account for as much mass as the central supermassive black hole in a galaxy. Most important for our purposes here, these intermediate black holes retain their initial dark matter spikes. These black holes are primary candidates to study for gamma rays and neutrinos that are produced by annihilations of the dark matter, now in the form of relic spikes. And if finding and detecting dark matter is not challenging enough, cosmologists today also are grappling with dark energy, an even more unexpected discovery.